repeat what we did last time. We derived Lagrange equations of motion. More precisely, of the second kind. But those equations of the second kind are classically called Lagrange equations. So we were starting with a potential energy V of x from Rm, and the movement was given by masses and g of x equals to 0, meaning the manifold M. That's what we have. And by introducing the parametrization, around some x0 from M, P, x equals to P of alpha from some omega 1 from R M minus S. The alphas are the parameters. Then their number is the number of degrees of freedom. And we derive the following equations. Excuse me. Well, L is equal to T minus V, kinetic energy, potential energy. Transform it in the new coordinates. So I put here the hats. So T hat is the 1/2 that means PT D well, D P T M P no. Which is equal to alpha M of alpha hat alpha. But M of alpha hat, this is sort of a transformed mass in new coordinates, which now has the components dp t or d alpha I m dp or d alpha j. That's the mass. And the velocity, the potential energy is simple. that is equal to V of P of alpha. And then we are, vas smo čekali. Da znate da vas čekamo, ostavili smo otvorena vrata. So. Linearized for small oscillations at x0, red, some j m hat from 0. Well, this 0 means that p of 0 is equal x0. Some x0, and down there are parameters. Alpha j, I j double dot plus 1/2 sum over j d v hat at 0 d alpha I d alpha j equals to 0. And as we know, there's both of those matrices, which we now can call thick M and thick K, are positive definite, then we have the standard oscillation problem we know from before. And now there arose the question, well, that's very nice, wonderful, but what about if I take another parameterization? This here will give me some numerical information about the oscillation. For example, the frequencies. Are the frequencies the same if I take different parameterizations? And then I put it as an exercise to you to prove it. But now we will try another approach, which will show you that this question can be answered in a completely different way. What we did here, we first made a general theory, local, and then applied it to small oscillations. And we got standard equations for the oscillations. But there is another approach which says, well, why use parameters? Try to linearize before you use parameters, before making Lagrange equations. Start at the original movement with Lagrange equations of the first kind, which are somehow better visible. They are in the original space where the whole thing is moving. So, direct approach. So So we start with the standard equations shortly written this way. These are the Lagrange equations of the first kind. You see, we have two numbers here, m and s. M is the dimension of the whole space in which everything is moving. S is the number of constraints. So the real number of degrees of freedom is m minus s. And that's the advantage of those equations. You have less parameters. And here you have not m minus s, but you have m plus s, unknown objects. These are the x's and lambdas. So you must, anytime you try to solve this trade-off consideration, so we take again x0 from m and also x equals x0 plus x prime also from m, and try to linearize those equations in this original form. That would mean that you also have a movement, a displacement in lambdas. What are x0 and lambda 0? How do you choose them? Well, you choose them as the solution of the equilibrium problem. That is dl x0 lambda 0 is equal to d v x0 minus lambda 0 transpose g x0 equals to 0. These are the equations you get from those by setting x double dot identically 0. That's then no movement, that's the equilibrium. The particle stays. And we know that psi t, second derivative of the function L, taken at this point is positive for every psi from the tangent space different from 0. This is our sufficient condition for a stable equilibrium. That means for a local, strict local minimum of the function v on the manifold. And now, we go linearizing. That's the most difficult thing, because it is so easy that you write down normally only second equation in the sequence, because the computation is so easy, but then you have to understand it. You have to take Taylor approximation of those functions as functions of x and lambda. So what's the development of this? I will write down Taylor formula. Take this first at the point x0 lambda 0. That's the first. That means lambda 0 t dg 0. Now, as a function of lambda and g, this is easy because it's just simple multiplication. Then you get plus lambda prime t dg 0 plus, and then you have to take the first Taylor approximation of dg. That's the derivative times the displacement. That means sum over j to m lambda 0 t d. This is partial and this is vector gradient. G over xj taken at the point 0 times the linear part, and that is xj prime. All other terms are of higher order, and this is the Taylor approximation of the first order for this function. So I will put here not equal, but approximately equal. That's what I mean. So, now the same thing, well, yes. And I will set this to be equal to 0. No, well, yes. Yes. No. That's the first part. And then I have to look at this. V of x, again, Taylor approximation is equal to d v of x0 plus the linear term in the Taylor expansion, and this is m d v over xj taken at x0 times xj prime. So these are two terms. And now I have to do the same here. Well, this means 0 equals g of x, 0 plus x prime, and this is approximately sum over j m dg over dxj taken at x0 times x. So these are the linearizations using the Taylor formula. In which space? Well, in the space R m plus s, where the variables are x1, xn, lambda 1 to lambda s. These are the variables with respect to which I did this Taylor approximation. So now I set those approximate equalities to equalities, which is not true. But I get a new system of equations which will then approximate, so I hope, the true movement. Yes. I encourage you to do this computation somehow, but not just 1 day or 2 after the lecture, when you forget what I was talking, and just looking at your scripts, so that you do it a sort of autonomously. So, okay, so now put that together. So I will have now my m x plus lambda t v g plus dv is now approximate to what? Well, this is easy. This is just m x dot prime, because x0 is constant. That's the easy part. Now, I just copy those lines which I have written there. So that is plus lambda 0t dg x0 plus lambda prime t dg yes, x0 plus sum j equals to m lambda 0t dg over dxj x0 xy plus, now comes the v. It was the, yes, that was this part. Now comes the other one. This is plus d v x0 plus sum j equals to 1 m v x j yes. And I will set now this to be 0. These will be now our approximate equations. But look, first of all, this and this cancels, because this is the solution of the equilibrium equation. So now, approximate of motion. This symbol here now has to be computed. What stays here is in fact a second derivative. It's a derivative of the gradient, and I have to put it down in coordinates. So, m x dot prime, the ith component, plus I write down this in components. plus. Now comes this here. This is a sum. Lambda k prime dg x0 dxy yes, and this k now goes from 1 to s because I'm summing up over the lambdas. This is the number of constraints. Yeah. I took the ith component and then I had to make a sum. Well, k. Yes. Now, is the first, second. Now comes a more complicated formula. We have now a sum over k and j equal to 1 going to s and m respectively. Lambda k 0, the second derivative of gk the xi xj prime. That's this. Sum, yes. The ith component of I has the ith component of this. Of the gradient. So, plus, there is one more term, and that's this. This is the sum yes, sum again over g over j equals 1 to m d double v xi xj. You have to take the ith component of the gradient. And that's what it is here. That is the linearization of the first part. And now I have to take this one. Which gives sum j equal 1 to m d gk over dxj x0 xg equals 0. That's what we have. It looks quite complicated written this way, but if you recognize the matrix formalism, then it will be much, much simpler. So let me now write this down in the matrix form. this now is just m times x double dot prime. That's easy. What's that here? You see, take those two together. No. Yes. Lambda and V, yes. That's it. Maybe I just first compute for you the contribution of those two taken together. Excuse me, there is some xj prime here. Oh, it's linear, you see, in variables xj prime, which are now the variables, and lambda prime, it's linear. Oh, no. That's false. Please correct this. There is no xj prime here. There is lambda k prime here. Okay? Oh, no. Those two. Well, this is just nothing else. What's that? That's sum over j equals 1 to m d2l over xi xj taken at the point x0 lambda 0 times xj. That's what it is. Now, I can write it down better. That's now d2 of L taken at the point x0 lambda 0 plus, now, you have here the first derivative once and here also once. Let me now just write down in the matrix form to remind you, what is dg ij? This is d1 g1 d1 gs dm g1 shortly written dm partial m over gs. So now this part here means that you are multiplying the vector lambda prime by the transpose of the gradient. That's it. And here we are multiplying the direct product of the matrix dg times this vector. So these are now formally written. It's just the same thing as here. Formally, in the matrix form, written the new system, which is an approximation, a linearization of our original problem. That means it is expected to be true or to be accurate if we have small movements around the stable equilibrium. And we know, we did it quite a time ago, that this will be true if the total energy is close to the minimum of the energy, because the energy law doesn't permit the system go far away from the equilibrium. That's known. So it is not just pure heuristics which we do here. We know that the movement is confined to a small region around the equilibrium and a small region in velocities around zero. So the Taylor approximation is reasonable. Well, as before, there is no proof. I didn't prove that this will be a real approximation of the true movement. The proof is sometimes almost impossible. Sometimes it is possible, but this is not the first time you will meet the situation where the theory covers only partly the thing you have to compute. So the justification of this new model will come from the measurements. You would look how it works in the practice. Nonetheless, it is sometimes very helpful if you can check these approximations directly by strict inequalities. That's sometimes possible. So, now let's do some small linear algebra. Let's write it down even more abstract, in a more abstract way. M x double dot plus ax plus b transpose lambda. I now drop the primes. Equals to 0, and here bx equals to 0. This is a system which is obviously linear. But, well, it's not a system of differential equations. It is partly differential, partly algebraic. But here we can do the elimination explicitly. Now, before we do that, we have to check something. What do we know about the matrix A? It's symmetric, because it is second derivatives. So it's symmetric, by the Schwarz rule. But we know more. We know that this matrix is positive, definite, on a subspace. And that should now be carried over. What do we know? We know that Ax psi t psi is greater than 0 if, well, on the tangent space. And that's what he says. That means, well, B psi is equal to 0. You see, in this case, we can interpret our new equations as true equations of movement, but on an approximate manifold. And this manifold is just the tangent manifold. If you take these equations are now standard Lagrange equations of first kind, but not for the movement of the original manifold, but on the linearized, and there's a tangent space. So in this case, the tangent space is equal to the manifold. Very well. So now we have to solve somehow this equation to eliminate superfluous variables. How do we do that? We know that this matrix B has full rank because of the regularity. Huh? What that means, full rank. What's the type of this matrix? This is something like that. This is M and this is S. So full rank means that the matrix B has the rank S. Okay. Now comes some linear algebra. The same is true, of course, for the matrix BT, because the rank is the same for the matrix or for its transpose. Now the matrix BT now looks this way. And I can do something which you should know somehow from your study, which is called the QR decomposition. So this is equal to Q, which is full, times what? R0. Where R is a upper triangular matrix of the size S, and it's non-singular. That's the point. Full rank of S means that the QR decomposition gives you a non-singular R here. So what now how can I write down this equation, Bx equals to 0? Bt is QR. So what's about B then? B is equal then to Q, to B is equal to R transpose 0 times QTX. If now I take this as a new variable, unitary transformations are apt to make new variables without any essential change. This is the inverse of Q. Q is orthogonal. Matrix. That means that Qt is equal to Q minus 1. Now, if I call this to be my new vector, new variable, and I write it down in components, block components, according to this partition here. Then that means this condition now is equivalent to what? It's equivalent to y equals to 0. Because RT is non-singular and it kills y. So the only variable which is left is z. So now, this here can be written better, in a better way. Well, I don't need that anymore. Okay. Now I'm trying to not to be too fast with this. I hope you will get it. So now this now is equivalent to what? To m q 0 z double prime. Huh? Now x x is equal to q y0. And I know that y is equal to 0. Plus aq plus q r0 lambda yes, equals to 0. So all this is now equivalent to this. Now multiply this by qt. It doesn't change the validity of the equation because it's non-singular. So we obtain now qtm q v plus qta q z plus r0 plus to 0. Now, these are new matrices. What do I know about them? I will write down this as M11, M12, M12 transpose, M22, plus I11, I12, I12 transpose, I22. In this way, I express the fact that the whole matrix is symmetric. Oh, wow. Easy. So, now, what I said that the matrix A was positive definite on the null space of this matrix B. That means that now this null space is now explicitly written down here. So that means that this times this times this should be just positive definite. And that means that this is positive definite. This block. Because this, when you multiply this, you just get Z transpose A to Z. So, now we get then our equations. We just write down in components, in block components. That means M12 Z double dot plus A12 Z plus R lambda equals to 0 and M22 Z double dot plus A22 Z equals to 0. The first equation looks complicated, but it's trivial. Why? Because we first solved the second one. And what is this? These are linear oscillations. Why? Because A22 is positive definite and M22 is automatically positive definite because it is a diagonal block of a matrix which itself is positive definite. So we end up again with a system of linear equations, differential equations with their typical frequencies omega I, and the whole matter we know how to handle such equation. And now we have Z, then you just put it here and you compute lambda. This first equation gives us lambda, which is mostly uninteresting in applications. Which is interesting is this. So what we did, we now explicitly eliminated our variables. And this elimination is more direct. We know how we got this A22 and M22. This elimination is a sort of straightforward. Not just arbitrary as in the general theory with Lagrange equations. Except if you know well your parameterization, if your parameterization has a physical meaning. That's a different point. So, well, let me stop here. I will have to discuss something about this, but I will do it after the break. I need just, well, a good quarter of an hour, okay, to say 10:20, okay, 10:25.